Hi everybody, I'm Natalie Fenner from Bangor University and I'm going to be taking you through nutrient cycling and isotopes. So if we just go through the structure of the module first, I'm just going to touch on IMTA's ecosystem approach first of all and focus on the environmental benefits compared with traditional aquaculture. And then we're going to take a look at how we actually assess these benefits and why it's important to know. And we'll go through the potential for eutrophication and global warming, and we'll look at how to sample IMTA systems, looking at analytical techniques, and then who contributes what and how to analyse that. And then finally, we'll just get on to optimising IMTA design and management. So I'm sure you've already had formal definitions of IMTA in the previous modules, not least from Bastien on the previous module 7. So a more informal definition perhaps is just that we're trying to recreate a simple ecosystem in order to increase diversity, profitability and sustainability of cultured aquatic species by adding other species to utilise wastes and purify the water. So eutrophication and greenhouse gas emissions are associated with feed production and uneaten feed in situ in relation to traditional aquaculture. And IMTA could be a solution to this by reducing feed input and therefore wastes and greenhouse gas emissions, and therefore making aquaculture more sustainable. But how do we actually know that IMTA is going to be more sustainable than traditional aquaculture, and how do we assess the different designs and species mixes of IMTA? Well, one way to do this is to measure nutrient losses from the system that are likely to cause eutrophication in receiving ecosystems and are likely to cause greenhouse gas emissions. And really the same principles apply as for any other ecosystem, so maybe eutrophication of freshwater lakes or carbon loss from wetlands due to land use change, for example. So the main cause for concern is usually the dissolved inorganic nutrients phosphate, which is a cation, and nitrate, which is an anion. And that's because these nutrients are usually limiting to phytoplankton growth in the receiving ecosystems. And so an input of these nutrients to the phytoplankton often results in an explosive growth, which is often referred to as a bloom of phytoplankton, and then the knock-on consequences of that, which cause eutrophication. And we're also quite often concerned with ammonium, which is a cation, because it's a toxic form of nitrogen, particularly to fish. Another organic carbon fraction of interest is dissolved organic carbon, because it causes eutrophication in downstream systems, and it interferes with water clarity because it's brown in coloration. And we might also be interested in measuring particulate organic carbon, or POC, and that's because it's a food source for filter feeders such as oysters and detritivores, and it also contributes to sediment carbon stocks. So these outputs or emissions represent the fate of feed carbon and nutrients. So in other words, what's left after being eaten and filtered by animals, absorbed by primary producers, and transformed by microbes. And they form the underpinning data for many of the simple equations through to complex models that you might have already seen. And these will be combined with animal and primary producer yield-related measures. And in a closed sequential design pond system, this is relatively straightforward to measure because the inputs and outputs can be isolated and therefore contributions quantified. So if you look at these two models presented as part of the Earthen Ponds Standard Model Guidelines, which was part of the Integrate project deliverables, you can see in the top model there, A in particular, it's very simple in terms of its design because all of the compartments are separated and therefore it would be very easy to sample the inputs and outputs. But how do we actually go about doing this? Well, obviously we need some samples of water and gas to work with, and ideally one would take these from all inputs and outputs regularly and frequently in space and time. And that's because, for example, growth rates and therefore uptake of nutrients and CO2 fixation by primary producers is likely to show temporal shifts driven by environmental factors such as temperature. And also spatial differences may be important to capture. For example, if you've got seaweed rafts acting as a hotspot for biogeochemical cycling compared with open water. So we would usually take water samples in bottles or vials, ideally glass rather than plastic, because glass doesn't leach materials into the water sample. And for dissolved inorganic nutrient sampling, we would usually filter at 0.2 micron pore size. And that's because it removes most of the microbes likely to consume or transform various species of nutrients. But filter size is important if you're interested in also measuring carbon fractions. So for dissolved organic carbon, you might want to look at 0.45 micron because 0.2 would remove a lot of that VOC. So we can then measure inorganic nutrients, anorganic carbon and N fractions of interest, such as DOC and POC. So one way to determine inorganic nutrient concentrations in water samples is via HPLC. So this stands for high performance liquid chromatography. And the advantage of this is that you can do multiple nutrients at once. So a suite of anions and a suite of cations, for example. If we wanted to measure carbon fractions in our water sample, we could make use of a total carbon analyzer, like this one in the top image, and that can measure POC, and then once your sample is filtered, DOC and DIC as well. Moving on to gas samples, we might utilise a floating chamber to measure whole ecosystem exchange. We can use inverted funnels to get an indication of ebullition events or bubbling events, which are quite random in space and time. We could take a sample of the water column and look at dissolved gases, or we could take a sediment sample and use respirometry, where we collect the gases coming off a sediment sample in a gas-tight vial. So to measure greenhouse gases, so CO2, methane, nitrous oxide, we would use a gas chromatograph, and we would usually then convert to global warming potential by multiplying methane by 27.2 and nitrous oxide by 273, and this is to account for their different potencies. And it allows us to express everything in CO2 equivalents. So for example, CO2 equivalents in milligrams per metre squared per day as a flux. So that then allows us to quantify the overall effect of the uptake and release of the 3 different major greenhouse gases. So if we move on now to designs of IMTA where there are far more species combined and co-cultured together, it's very difficult to determine contributions of each compartment. And that's because the inputs and outputs cannot be isolated very easily. And this leads to 3 major problem areas. So the first is that we cannot easily differentiate commercial feed utilisation compared with the use of primary producers, for example in omnivorous fish. The second problem is that we cannot easily quantify uptake of CO2 by primary producers compared with production via microbes, etc. And the third problem is that eutrophication effects due to aquaculture effluent may be confounded due to multiple sources downstream, so for example agricultural runoff or sewage outfalls. So one tool we can make use of to solve these issues is stable isotope analysis. And this is making use of differences in ratios of heavy to light isotopes of elements of interest. So carbon or nitrogen in this case, naturally occurring in the environment. And these are caused by different biological and physicochemical processes that fractionate or discriminate against the heavy 13C isotope, for example, leaving a characteristic signature when expressed in relation to a standard as delta 13C parts per mil notation. So photosynthesis, for example, will utilise CO2 from the atmosphere, which is usually about -8 parts per mil, and as it takes that CO2 up, it will fractionate against a heavy isotope. So this will lead to tissues in phytoplankton of -20 approximately, but in seaweeds this might be -15 parts per mil, depending on things like environmental factors. So it provides a useful difference that can be used to trace carbon through a food web. And we might use it to determine what fish are eating, either pellets or phytoplankton, if there's sufficient difference between those sources. And it's the same principle from large mammals all the way down to tiny microbes. So, for example, a herbivore will have a signature more like grass, usually very negative, compared with a carnivore that's eating meat, of course. And methane produced by methanogens, utilising carbon from feed pellets, will be very different from those utilising CO2 as a substrate. And this is often combined with delta 15N, which indicates trophic position in a food web. So we can see from this slide, if we use fish meal pellets for feeding trout, there is a delta 13C signature of -21 in the fish meal, and that then becomes -20 in the trout mussel. And there is this predictable enrichment from food source to consumer of about +1 part per mil in 13C, and that is more like +3.5 in terms of delta 15N, which, as I mentioned before, indicates trophic level rather than flow of nutrients. We can also use delta 15N to assess nitrogen sources that macroalgae use. So we know, for example, that seaweed will utilise ammonium from mollusk wastes. And we know ulva is often an excellent bioremediator due to its very fast growth and efficient uptake of things like nitrates and phosphates. And macroalgae are a very sensitive indicator of nitrogen sources in aquatic systems, and natural and anthropogenic nitrogen sources, including inorganic fertilizers, sewage and manure, differ in terms of their delta 15N values. So we can often determine the pollution culprit. So those problem areas 1 to 3 have now been solved in that we can reconstruct trophic webs, we can assess different species mixes, we can determine gas pathways and contributions from different organisms, and we can assess the impact of nutrient pollution sources. But to actually do this on the ground, we'd need to employ isotope ratio mass spectrometry. And what we would do is we would sample our tissues, so animals or macroalgae or perhaps sediment. Then we would freeze dry that material, grind and homogenize it, weigh it into tin capsules, and then analyze it using our IRMS system. And we'd need an elemental analyzer interface to analyze the solid samples and a trace gas interface to analyze gases. Okay, so why is all this useful to know? Well, knowing the fate of feed in a system allows us to optimize commercial feed quantity addition versus utilization of, for example, phytoplankton as a food source. And so it increases the environmental benefits and profits because less is wasted and therefore emitted. And we know, for example, that feed promotes methanogenesis via acetoplastic pathways in anaerobic sediments. And it also allows us to select optimal species for maximum bioremediation of nutrients. So, for example, primary producers with fast growth rates, or perhaps least emissions, or a combination of both. And it can also inform management of our IMTA systems. So, for example, removal of uneaten feed may reduce methane emissions. We may want to consider artificial aeration or addition of primary producers that have high oxygenation rates. Or we might want to harvest certain seaweeds much more frequently to allow more rapid nutrient uptake and bioremediation of nitrate and phosphate, for example. Okay, so just finally then, I'd like to highlight this paper by Nahon et al. 2023, because this really provides a nice case study combining the stable isotope analysis technique along with routine measurements and also fatty acid analysis. And what they've done is investigated 3 different IMTA designs and also the roles of species within those models. So it provides this nice case study for furthering knowledge of interpretation of results and also identifying knowledge gaps that perhaps we still need to fill in IMTA. So that's it from me. Here are the major references that I've mentioned in this presentation. And just finally, here is the contact information for the Integrate IMTA project. Thank you very much.